Alright, hey guys, what's going on? So today we're going to be going quantum with our gauge fields. And the way we're going to do that is we're going to look at our completeness relationship as an operator now. But before we do that, just to recap what we've done so far, we have talked about the completeness relationship. We sort of looked at it as some sort of analog as to what we've seen, as to what you might see in something like GR. We've also essentially what the completeness relationship was a relationship between our structure constants, or in GR what you might call some things that look like tetrads. We've seen a relationship between those and what looked to be an arbitrary equation involving the Minkowski metric and the momentum of the particle that we're studying. What we want to do now is we want to take this to the quantum level. The way we're going to do this is we're going to make this an operator, right? So in quantum mechanics, again, the theme in quantum mechanics is to make things operators. And by doing that, we'll discover a few new things that are very, very interesting. And we will be able to really parse out exactly what this arbitrary looking equation that we came up with yesterday, or not yesterday, but a few days ago, what it does when it becomes an operator, right? So make sure to hit that like and subscribe button, and let's get right into the video now, or the content. So when we are going quantum with our gauge fields, the natural inclination is going to make this thing an operator, right? So we're making the completeness relationship an operator. So here's the operator, right? So this is what we've seen before. We'll take a look at the other side of that equation later. But right now we're going to call this just an arbitrary operator P mu nu, okay? This P mu nu is going to act on some arbitrary vector. We'll call it a velocity vector for right now. We'll just call it an arbitrary vector, okay? So this arbitrary vector is going, when it's applied to our P mu nu, let's see what happens. So here's our P mu nu, we're applying it to our V, our arbitrary vector. When we apply it to the Minkowski metric, right, this is just going to be some index contraction going on. And when we apply it here, right, so this just comes into the brackets, right? So putting it right here. And by doing that, we are going to call this thing a new arbitrary vector. You might think, okay, two arbitrary vectors. What the heck's going on? Well, what's going to happen is that, okay, say we now apply this new arbitrary vector to our 4 momentum, okay? When we do that, we're gonna see our 4 momentum show up right next to this guy, so that's gonna be here, and we could put it right in here also. We could put it really anywhere. A good place to place it, though, is going to be next to this K mu, because what we'll find out is that this and these two guys are the same. Those will cancel, right? These is m squared, this is m squared. So what we get is this minus this, which is essentially the same thing, right? These are two inner products of the same vector, okay? So that's going to be 0. So essentially, when this is applied to this arbitrary vector is applied to our 4 momentum, that gets us 0. But our arbitrary vector, we said was this, right? So this is the relationship. So the completeness operator selects out the part of the velocity, or this arbitrary vector, not the velocity, of the arbitrary 4 vector, selects out the part of the arbitrary 4 vector that is orthogonal to the momentum 4 vector of the particle. right? And this really only works for the momentum forward vector because of this relationship. And so, for a massive particle moving in the z direction, our momentum forward vector looks like this. Our arbitrary forward vector, therefore, has to look like this, right? Because when we do this, we're going to see that this must equal 0, right? So this times this has to equal 0. So in order for that to happen, this is going to be 1, right? 0, 0, and then this has to be minus 1, right? So this guy times this guy's going to be minus 1. That's how we're going to get 0. So this is what that arbitrary forward vector looks like, okay? Now, let's deal with the other side of the equation. The other side of the equation is this thing that we looked at before, right? So we said this was some momentum, or not some momentum. We said that this was the operator that we were dealing with. Now we're looking at this side of the equation. In quantum mechanics, the completeness relationship looks something like this, okay? So if you've taken quantum mechanics before, this might look very, very familiar to you, right? This is what's called the completeness relationship in quantum mechanics, and it basically tells us that the sum of the inner product between Braun-Ket vectors describing the same state is 1. It's basically saying that the sum of all probabilities goes to 1. And this looks very reminiscent of something that might look like this, right? So these two things are the same, these two things are the same, and we found out that it was equal to this. And so these two guys, which are vectors in some Hilbert space, again, because again they made up this little, we constructed this little orthonormal basis vectors in which our particle was traveling, right? Our particle was traveling. So these are vectors in a basis in some Hilbert space, just as these guys were some vectors in Hilbert space. This is what's making this a vector field, right? These aren't spinors. These aren't scalars. These are vectors. And so in this picture that I've brought up many times now, we find out that, okay, we have an orthonormal basis vector. Those are these guys. These are the guys that we've constructed each point in space and time. We also have our 4 momentum vectors that's helping us define exactly what this is, right? Because we need to be able to say the particle's traveling in z. Okay, when it's traveling in z, now we can construct an orthonormal basis, right? And then we had some arbitrary forward vector that helped us link the completeness relation helped us understand the completeness relation in the context of it being an operator, right? And so with all of that being said, that's sort of what I have in this video. I want to really press this because we looked at, again, where is it here? We looked at this operator, again, what it did. This operator here takes 2 vectors, brings it to 0. That's kind of interesting. We might want to think of that as a tensor, maybe, something to think about. This operator, again, it operates on something, brings us to 0. And similar here, this guy here, operator, essentially not multiplying by anything. This is an operator, and it goes to 1. So there's this interesting relationship where this guy, when it is applied to an arbitrary vector, and when that means this guy's going to have to get applied to an arbitrary vector, they're going to bring some that arbitrary vector, or they're going to make that arbitrary vector such that when it's applied to the momentum, we get 0. Okay? That's the whole point here. The momentum forward vector. we get 0. Right? So I'm not saying that there's a complete analogy between, I'm not saying that there's a complete direct link between this, what looks like a quantum mechanic completeness relationship, and this relationship between, this relationship right here. I'm not saying that there's a direct link between the two, because there's obviously not. This guy brings us to 1. This guy should bring us to 0 if it's applied to our vectors. So there's obviously not a direct link between the two. However, just like we looked at GR, there's an interesting relationship there's an interesting analogy that can be made here in the world of quantum mechanics, in the world of GR, and the clashing point seems to be at this relationship right here. Okay. So we've sort of been beating up this idea of a completeness relationship for about 3 videos now. What we're going to do next is we are going to take a look at the solution to the gauge fields themselves. We're going to look exactly at, we're going to diverge a little bit from this, but we want to keep this completeness relationship in mind because we're going to use it in deriving the creation and annihilation operators for our gauge fields. And when we get those creation and annihilation operators, we've essentially brought ourselves home, right? It's the goal that we want is the goal that we're aiming for again is the creation and annihilation operators. What exactly they look like? What exactly is the right relationship between them, right? Because when we do that, like we've seen in the Dirac field, when we do that, we can then say, for example, in the case of the Dirac field, derive the Pauli exclusion principle, right? That's when we demanded our relationship between the creation and annihilation operators, we were able to derive the Pauli exclusion principle. So the relationship between those is really, really what we are looking for. And so we're going to do that in the next video with our gauge fields. And so with all that being said, I hope you guys enjoyed that video or enjoyed this video. And I'll see you guys in the next one.